Hello, and thank you for joining us. My name is Mindy Weisberger from Science Bulletins at the American Museum of Natural History in New York City, and we're pleased to be doing this Hangout on Google+, along with NOAA climate scientists in support of our new data visualization, Ozone Slow Recovery. Before we get started, whether you're watching on Google+ or on YouTube, we'd like to encourage your participation. If you have questions at any point, please submit them in the comments, and there will be an additional opportunity to ask questions at the end of the presentation. And with that, I'm going to turn this over to Laura Allen, Senior Editorial Producer for Science Bulletins and the writer and producer for the Ozone Data Visualization.
Hi, everybody. I'm Laura, and we're really pleased to have you here today. This visualization is as a segment of a program at the American Museum of Natural History called Science Bulletins, and what we do is report on current science happening all around the world through video and visualizations. So I want to welcome you. We've got a lot of folks on the line watching that are educators at museums and science centers, probably some formal educators as well. And we're all going to be able to have the opportunity today to look at this visualization that we've updated for 2013. It highlights ozone's patterns around the globe, the 2013 ozone hole, and highlights the outlook for the ozone layer going forward. So what we're going to do in the next 45 minutes is to show some excerpts from this visualization and use those as jumping off points. We're going to explain the scientific data that you're seeing and give a broader context so that if you're interested in using this piece with your audiences, you'll be able to dive deeper and be able to understand and explain what you're seeing and a little bit more clearly, and so that you can reach out. We're happy to have two ozone scientists from NOAA joining us today. We have Craig Long and Bryan Johnson. And so before I introduce them a little bit more fully, I just want to say where you'd be able to find this visualization. We are now showing the visualization here at the American Museum in our Hall of Planet Earth, and it'll be up for a couple of months. We also have put it up on amnh.org, and that'll be available indefinitely. We also have formatted this piece to wrap around the Science on a Sphere system and other spherical displays. So this can run as an auto-run piece. We've got the text and the legends in that, so you can use it that way. Or if you are part of the Science on a Sphere community and are interested in producing and making live programming, we invite you to adapt it and play with it and use some of the information that we'll tell you today to do that. So links to both of these versions can be found on our Google Plus page, and you can look there for other resources and more information as well. So I'd like to also thank NOAA. They're the funder for this visualization series and this outreach. So thank you, NOAA. So let's meet our panelists today. We've got Craig Long. Craig is a meteorologist at NOAA's Climate Prediction Center in Maryland. Craig analyzes data from both NOAA and NASA satellites that monitor stratospheric temperatures and ozone around the globe. And he also leads NOAA's annual bulletin that is assessing the ozone hole each year. He also helped pioneer the UV index forecast. You might see this in the paper. This is related to ozone assessment, so we're going to get to that a little bit later in the broadcast. Bryan Johnson is here with us as well. He's an atmospheric scientist with NOAA's Earth System Research Laboratory, and he leads NOAA's efforts to assess ozone weekly at 9 sites around the globe using balloon-borne instruments called ozone sondes. And he'll talk a little bit more about that. One of the most interesting places they release the ozone sondes is the South Pole, and that's obviously very relevant to assessing the hole. So we'll get to that a little bit later too. So all the while, I encourage you to ask questions. We'll weave them into our conversation, and you can ask them at any time. All right, so before we turn to this visualization, I'd love to start off just by getting real basic. Craig, what is ozone, and where is it found in the atmosphere, and what does it do for us?
Okay, hi. Ozone is a triple atom molecule of oxygen It's mostly found in the stratosphere. It is found in the troposphere, but the primary place is up in the stratosphere. It's as I said, it's the three atoms of oxygen. It has a creation cycle of the UV light coming from the sun into the stratosphere and breaking up oxygen molecules and releasing one of those atoms, and it joins with another oxygen atom to create an ozone molecule. The ozone molecule itself gets separated quite a lot with UV light and thus releasing heat, and that's why the stratosphere increases with temperature above the troposphere. So why is it important? Well, just as I said, because it's using the ultraviolet light to break the atoms, these molecules apart, and in so doing, it's absorbing all the UVC and part of the UVB part of the spectrum, and that helps us down at the surface survive. If we didn't have the ozone layer, then, or if we had a reduced ozone layer, then much more UVB radiation would be reaching the surface, and increase in cataracts and skin cancer, and lots of bad things would happen to all the flora and fauna around the world.
Okay, great. So, so ozone in the troposphere, that comes from a different source, and that is considered unhealthy as well, right?
It's primarily a product of air pollution.
Okay.
And when breathed in, it's caustic to the lungs. Yeah.
Okay. So we're going to be focusing on ozone in the stratosphere for this this visualization in the 45 minutes here. So let's actually turn to the visualization itself. I'd like to show ozone varying around the globe in space and in time. Is everybody seeing that? Okay, great. Craig, jump in.
It's a mixture of instruments from that NOAA runs. It's using the SPUV and one of the IR instruments to do a better job of creating a total ozone estimate. And so it's portraying the atmosphere, the ozone column in the atmosphere, the colors that you're seeing around the globe they're varying with time, and as we go in towards the ozone hole, they should be getting redder.
So let's show. This is a series of daily images from May 2012 through September 2013, and let's run that a bit. Now we're seeing some patterns around the Earth.
Yeah,
here we're seeing ozone, lower instances of ozone towards the South Pole. And there are some spots around the equator as well. So what are some of these patterns that we're seeing, Craig?
Well, in equatorial region, that's naturally lower ozone. Ozone is created in the equatorial region, and the circulation patterns in the stratosphere take the ozone away from the tropics and move it towards the poles. So it's naturally lower ozone, and that's why it's showing up in those orangey red colors there. But but here now in the South Polar region, the yellow line indicating an amount of 220 Dobson units, and then the red values showing values smaller than 220 indicate the ozone hole, or where there's vast ozone depletion. The reason why we choose 220 is because before the ozone hole existed, there weren't really values that low in the South Polar region. And what a Dobson unit? A Dobson unit is a measure of how we measure ozone in the atmosphere. If you compress all the ozone in the atmosphere down to the surface, and at 0 degrees centigrade, it would measure just about 3 dimes thick. The ozone hole is only about 1 dime thick. So that's a measure of how small the ozone amounts are in the ozone hole region.
Okay, so it's not free of ozone. There's just a much lower density of ozone in that region.
That's correct.
All right. So briefly, can you say a bit about how satellites take these total ozone measurements around the globe? How do they detect ozone in the atmosphere?
Well, there are various ways, but the most common way that we use is by measuring the amount of ultraviolet light that is scattered back from the Earth to the satellite. We measure how much is coming from the sun, and then we measure how much is coming back from the Earth, and it's a ratio, and from that ratio at different wavelengths we can determine how much ozone is in the atmosphere, and also how much ozone is in the vertical part of the, not only the total ozone amount, but how it varies in the vertical.
Well, that's actually a nice segue into what Bryan does. So, Bryan, tell us a little bit about what your ozone sonde balloons do at the South Pole and other places around the world. How do they get a different picture of ozone levels at point sources around the Earth?
Yes, well, while the satellites are circling the globe and looking at a big picture, we're getting more of a detailed view of the ozone hole from releasing balloons. It's like National Weather Service balloons that they release to look at profiles of temperature and pressure and wind. We're actually doing something similar, but we put an ozone instrument on that. So this balloon, we don't need sunlight, and all we need is the wind's low enough to release the balloon. So the balloon goes up at about 10 miles an hour. So in 2 hours, it gets to its peak height, about 20 miles high. And then the balloon bursts and comes back down. But while it's ascending, we're getting data back by radio signal. So we're getting a very detailed picture vertically of the ozone layer. And at South Pole, we start to go into the ozone layer at about 8 miles high and then go out of the main peak at about 14 miles high. So we get a really good detailed picture because this ozone sonde is sampling air and measuring with a special chemical sensor that we can then see the details of the ozone layer.
So I'm showing some of those images of an ozone sonde ascending through the atmosphere. Can everybody see those? I've got one from Boulder, Colorado, from the ground, and then a higher atmospheric image, 7 to 8 miles above sea level, and atmospheric pressure is dropping here. And then this is what the balloon's eye view, it looks like at 18 miles above sea level in the stratosphere.
Yes, and so that's on that particular launch, one of the places we launch it here in Boulder, Colorado, once per week, and we put a camera on board that we recovered later. Usually the balloons will land about 30 to 60 miles away, and it just kind of gives you a perspective from what it looks like on the balloon and where the ozone hole is. That airplanes usually fly, you know, at about the 32,000 foot level, and we're not quite in the ozone layer at that point. But then once we get up to that 18, 20 miles, we're beyond the main ozone peak, and when you look out horizontally, you can start to see the darkness of space. It seems like you're a long ways up, but in relative to the size of the Earth, it's really the atmosphere is really kind of a paper thin. If you hold a globe in your hand, it would be like the size of a sheet of paper. So even though it seems like we're far up, the atmosphere is a pretty thin layer. But that's the perspective that we see from when we're on an ozone sonde balloon.
Excellent. So let's talk a little bit now about the ozone hole, its past, its present, and its future. I'm going to cue up the visualization again. So let's look at a snapshot here of the maximum size of the ozone hole this year. It reached its maximum size on September 22nd, 2013, and we'll scrub forward and look at some of the ozone holes in years past. So this was the ozone hole in 1982, right when it was emerging. And then we'll cue forward, and this is the ozone hole in 1987, right when international agreements were starting to be signed to do something about it. And then we have the monthly average of the ozone hole in 2013. So all of these three images, just to clarify, show the monthly average. It's the average of all the daily images between September 15th and October 15th, which is why it looks different from the ozone hole max on the single day image on September 22nd. So, Craig, you were working at NASA on clouds when the ozone hole, the news on the ozone hole started to come out. What was the reaction from the scientific community? What did people think was going on?
Well, NASA had launched a satellite in 1979 to measure total ozone, and they had been monitoring the ozone in the atmosphere for several years by the mid-1980s. And they had seen low ozone amounts over the South Polar region and weren't quite sure if this was something wrong with their algorithms or something was amiss. But at that same time, the British Antarctic Survey had also been monitoring ozone at the surface with instruments and had also been seeing this decrease in total ozone over the South Polar region, and they published a paper in 1985, and NASA went back and re-evaluated their observations and concluded that yes, they were seeing the same thing, and because they're using a satellite, they have a much better 2D picture of the extent of the ozone hole. So actually, they had seen ozone decrease back in the late 1970s with an earlier satellite. So so now their instruments are kind of like the de facto standard for measuring total ozone in the atmosphere and how we monitor the ozone hole.
And so what's happening here? What is happening with the buildup of ozone depleting chemicals at the South Pole to cause this intense destruction?
Well, the ozone depleting chemicals are throughout the entire atmosphere. There is some there are natural types of ozone depletion, and then these ozone depleting chemicals are also decaying ozone outside the polar region. Inside the polar region, the combination of several factors, the air temperatures there are ultra cold. The air is confined to the South Polar circulation, so there's not a lot of interchange between the outside air and the inside air in that polar region, and a unique chemical reaction that occurs on clouds that are occurring in this polar region when the air gets very cold. And that reaction quickly strips ozone, the oxygen molecules away from the ozone, and very quickly depletes ozone in the polar region. So it only occurs in a specific height region. There's still ozone towards the surface and higher up, but in the middle part, as Bryan's observations show, that the middle part can be completely void of ozone. And
those of you who are joining us from the Science on a Sphere community, just recently released today was a couple of data sets on the polar vortex. Those data sets could be used to show that circulation of air that corrals the ozone hole and creates that intense region of ozone loss, or helps keep it in place. So that's just another type of data set you might be able to use for live programming if you're putting something like that together. Let's try to queue up a graph here of the past ozone holes in recent years and look how the 2013 ozone hole compares. So how does the 2013 ozone hole, how does that look compared to recent holes that we've seen? I know that the ozone hole can vary every year quite a lot.
That's correct. The ozone hole is not only a result of ozone depleting chemicals, but it's also regulated by the meteorology that's going on in the stratosphere at the time. So the size of the ozone hole and the shape can vary quite a bit from year to year. As we look at this diagram, we can see starting in '79 through the 1980s, the size of the ozone hole grew practically every year. There's a little dip in '86 and '88 because of the polar region was very warm in those years, and then it begins to flatten out in the 1990s. And then, so the last 2 years, 2012 and 2013, are rather on the small side of ozone holes in past recent years, and that's primarily due to the amount of the warm temperatures in the polar region. And so, but a year before, in 2011, it was rather large as far as ozone hole goes, and that's because the temperatures were colder. So in essence, the colder the temperatures are in the polar region, the more stable the pore circulation is. You'll have a larger ozone hole. In years where the temperatures are a little bit warmer, and if there's some irregularity to the flow of the pore circulation, then you'll have smaller ozone holes, and they may not last as long either in that year.
So, well, now let's think going forward a bit. Where are we in ozone hole recovery, or the recovery of the ozone layer writ large? There were international controls put in place, new agreements signed in the late 80s, and when are we seeing a decrease in the amount of ozone depleting chemicals in the atmosphere, and how might recovery of the ozone layer follow from that? And maybe Bryan, you can jump in here.
Okay, yes, one thing that's fairly simple to measure in the troposphere, or the lower atmosphere, is the chlorofluorocarbons and the CFCs. And those are basically the carriers of chlorine that bring it up. Eventually they get up into the stratosphere. It takes 3 to 5 years on average probably for emissions down here or gases from CFCs to make it up in the stratosphere. Again, these are really long-lived gases. They're 50 to 100-year lifetimes. But once they get high up in the stratosphere, then they break down pretty quickly with the ultraviolet or strong rays from the sun. So right now we're measuring and seeing that the ozone depleting gases, or the ODGs, they are declining. And so that's a fairly steady stream or steady downward trend. But it's slow, and it's going to take a little time to get back to where we were in the pre-1980s levels. So ozone then will oscillate along that graph, going up and down depending on the conditions for the year, how chlorine is processed, what kind of ozone hole are we going to get, be colder or warmer, or the vortex stable. And in the last couple of years it has been warmer, and so we haven't seen quite the ozone hole that we have in other times, but there's still the potential. There's still chlorine there. That's the main ingredient, and that takes a little while to for the atmosphere to kind of naturally deplete itself or get rid of the chlorine up there. So we're on the right track. Everything's looking good. Just taking probably another 10 or 15 years before we really, at South Pole, for instance, start to see that yes, we're on the way to complete recovery. It'll be another 40, 50, 60 years from there. No ozone hole.
So we have a segment showing that in our visualization, showing the projections for ozone recovery. These are based on computer models, and I'll play that sequence right now so you can see what this might look like moving forward. So with these animation that we've produced here, like I said, is based on a computer model projection on a graph, and we've indicated the uncertainty of that projected size with a fuzzy boundary around each future ozone hole at these key decades in the future. Now, will the ozone hole and the level of ozone generally in the atmosphere have different recovery rates?
Well, yeah, in the outside the polar regions, the ozone or the ozone depleting chemicals should be. I'm looking for the right word. They should be depleting themselves at a little bit higher rate than over the polar region. So globally, we might see a recovery in maybe about 10 years or sooner than we would in the South Polar region.
Okay. We're not at the point where we can really say that we're seeing recovery just yet, right? I mean, we expect that we'll be able to see the size of the ozone hole changing this decade. What is it going to take to be able to really firmly say that the ozone hole is on its way to a shrinking trend?
Well, as has shown in that graph, there's lots of variability, and with that variability, the statistics of knowing for sure that trends are on the smaller side, that it takes a good 10 or 15 years to show that through the observations that the ozone hole is recovering and it's getting smaller. So this plot that you're showing now, this is a plot that was taken out of the International Ozone Assessment, and it kind of shows very nicely and in general terms what we expect as far as the process, the ozone depletion on the far left side, the reaching its minimum value at the bottom of the curve, which occurred in the late 1990s, and so we're just a little bit 10 years past that, but we're on that long slope upward of ozone recovery, and as you can tell, the width of that orange band gets larger as we go forward in time, and that's indicative of the uncertainty that we know of things, whether or not climate change has a role in the ozone recovery, and but we expect to get to 1980 levels by the middle part of the century, or just a little bit past the middle part of the century.
Great.
And I can add something for ozone sounds. Yeah, from South Pole, then when we release ozone sounds, and what we look for recovery on some of the details is right in that ozone layer where most of the ozone is located and most of it is being destroyed. Around the nice thing about South Pole, it's right usually in the middle of the ozone hole, and so we're able to see from right in the middle what the generally the worst conditions are. So we track around September 1st, ozone levels in the ozone layer start dropping very quickly, day by day, and that's a picture here of column ozone from the British site. So. And what I'll say about that is in September 1st, it's amazing. It's just like falling off a cliff. The ozone starts to drop very quickly, and that's when the sun rises and starting to hit the stratosphere and initiate all this chemistry that releases the chlorine to destroy ozone. And by the end of September, and sometimes in that 9 to 13 mile layer, in a really bad year like 2006, there'll be essentially zero ozone. and this year wasn't quite as bad. But we're watching it for is how fast does ozone decline in September. When we start to see the rate of ozone decline start lessening or not quite as fast in those first 3 weeks of September, then is when we'll probably start to say, okay, we're on the road to recovery now. It's looking pretty certain that we're doing well. The CFCs that have been controlled by the Montreal Protocol, that's our best step, is limiting the emissions of CFCs that we can do. Now it's just waiting it out, let nature kind of work with us and to take some time.
And the Montreal Protocol has really been lauded as one of the most successful international environmental agreements to date. Isn't that right? The cooperation that was involved in making this, pulling this off.
Yes, I think that the speed at which everyone kind of came together globally to look at what's going on and decide what steps we need to take, and yes, the results happened very quickly that to limit the emissions of the specific CFC 11 and CFC 12, some of those chlorofluorocarbons that have these longer lifetimes that are going to hang around and build up. So that was definitely a milestone in cooperation globally.
So I have a few more questions for Bryan and Craig, but I will encourage anybody to ask a question that might not have been answered yet. Reach out on our Google Plus page for the event or the YouTube page with a comment, and Mindy will help feed that to the scientists themselves so they can answer your burning questions about ozone. So both of you have mentioned to me a new satellite, a satellite jointly managed by NOAA and NASA called SUMI NPP, and this is now sending new images of ozone down. We're just now being able to use that data into interpretation. How might that satellite improve or give us a better picture of ozone globally and at the polar regions?
That's correct, Laura. This satellite is a new generation of ozone sensors. The sensor is called a OMPS, and it continues the heritage of previous ozone sensors, the vertical looking instrument that NOAA has had for 30+ years, and the total ozone measuring instrument that the NASA has had for the same amount of time. And in addition, there's a new sensor on this satellite which looks backward and at the limb of the Earth and can measure ozone in much greater vertical detail than what we had been able to do before. And so what the great thing about that is with that instrument we can look better at the ozone recovery, where it's occurring in the atmosphere, and with much greater detail in the vertical. With the previous instruments, the vertical resolution was a little bit large, and so we couldn't quite get the details that we're looking for in ozone recovery. But this satellite it's very exciting that it's working very well. NOAA and NASA have been working for years together on ozone situations. So we have this great partnership, and so together we've been able to have a pretty good idea of not only how the ozone's been depleting and recovering around the Earth for the past 30+ years as far as total ozone, but we have also been able to look at in the vertical how it's been varying as well. So
great.
So we just continue that on for the next 20 years or so.
So we got a question from Elke. Which countries are still allowed to use CFCs, the chlorofluorocarbons, if any?
Well, it's well relegated to what you would call third world countries, countries that are still trying that can't afford the newer chemicals. So there's some allowance for these third world countries to to use these chemicals. I don't know exactly what the purpose of what they would be using these chemicals for, but there's just a certain allowance, and I presume that over time that they too will be asked to abide with the protocol.
Okay, so nearly all countries have signed this agreement, though, the Montreal Protocol and its follow-ups limiting the use of chemicals, and they're in, classically, they've been in refrigerants, and what other types of uses have CFCs been?
Well, CFCs were, yes, they're very good at refrigerants. It's at the surface, it's a relatively inert gas. So it has a long lifetime, and as I said, it's a refrigerant. It works really well. We used to call it Freon. It's also good for, or was used in aerosol cans. It was great for propellant, and also for electrical equipment. It was good for cleaning those instruments and during the manufacturing process. There's not only are CFCs dangerous, but there were also some agricultural chemicals that are dangerous as well. Methylbromide is now a highly regulated chemical that was used in agriculture to kill bugs and things like that. But bromine is actually more destructive than chlorine in ozone, so that those chemicals have been regulated as well.
Great. We actually have a question which is related to the one that I have about climate change. You know, sometimes we see misconceptions that somehow global warming is causing the ozone hole. But what is are there any links between climate change and ozone levels? And the question specifically was, will the atmospheric changes due to climate change distribute the ozone hole or the holes differently?
Yes, Laura, I think there's a slight connection, but the main thing about the ozone hole, to remember the three key ingredients, and that is chlorofluorocarbons, or the CFCs, that make it up into the atmosphere. How long will it take for those to deplete, for this atmosphere to deplete those? Then there's how cold does the atmosphere get over Antarctica in the stratosphere, that upper atmosphere, to process the chlorine effectively to destroy ozone, and then of course the sunlight coming up. So the one thing where climate change could have an effect is on the temperatures and the stability of the polar vortex. If, for instance, the surface or troposphere warms, it's just the way the Earth works in separating it out in layers of radiational balance, that when the Earth warms at the surface, it gets a little cooler up in the stratosphere. And so with a cooler stratosphere, you have a higher tendency to produce more effectively the polar stratospheric clouds that form. Generally, they don't form most any location except over the Arctic or especially the Antarctic. So if you can always have these prime conditions, a stable vortex and cold temperatures, it might allow the ozone hole to be a little worse each year. But the main thing we're watching is that the chlorine levels continue to drop.
So the chlorine levels are obviously the primary driver here.
Yes.
So two more questions, actually. We're getting a whole bunch right at the end of the broadcast. Let's see. Let's start with one related to the last question. What other atmospheric regions are prone to low ozone levels apart from the South Pole? You mentioned periodically or rarely the Arctic can see a drop. What about other regions? Are there familiar patterns that we see with low ozone?
I'll add a little bit more to that. In the Arctic, we don't have quite the stable vortex and cold temperatures, but if the right conditions happen, like in 2011 in the spring, we did get an image of what an ozone hole can appear in the Arctic, and that means just lower than normal ozone levels. Around the rest of the globe, there's just a lot of mixing and and natural conditions, it's very hard to get an ozone hole to happen. It's unusual that the tropics actually have lower ozone or total column above you, just because the transport out from that region toward the polar regions where ozone gets built up in the stratosphere. But there's no holes, it's just that it's lower over the tropics and then builds up mid-latitudes, and springtime Arctic region can see higher levels. So we really don't see a hole, it's just in mid-latitudes or tropospheric areas. But what we're concerned about sometimes, though, is just the mixing of the ozone hole into the rest of the atmosphere may decrease ozone slightly, or if you have little blobs of it drifting over different countries for briefly a few days, you might get a little more UV if it's in a higher sun angle region.
Okay, I actually queued up, I'm not sure if it's coming through, but I queued up a web page. This is a NASA image showing that the Arctic actually experienced a bit of an ozone hole in 2011, as Bryan has indicated. And now these colors are opposite what we used in our visualization. Data comes in on a grayscale, and we apply the colors that we feel brings out the properties and the messages we want to send about ozone. You can see that NASA chose to use blue for low ozone amounts as opposed to red in this particular visualization. So we can see a bit that there was a hole over the Arctic, similar but not as intense in March of 2011 as there typically is over the Antarctic in September and October. Now, before we wrap up, I have one last question I'd love to get to. Referencing the question about which countries have the ability to still use ozone-depleting chemicals, do either of you know if there's a concrete time limit set for when they need to phase out those chemicals, or is that still under discussion?
Go ahead, Craig. I'm not sure about that. I think, the major economic countries in U.S. and European countries, I think they've pretty much followed as quickly as possible the restrictions, and there may be a few rogue areas producing CFCs, but it's just not something, I don't think, that's produced very, probably not significant quantities like it was in the 70s.
Right. Personally, I don't know what the timeline is for these countries that are still allowed to have CFCs. Of course, we want to have total non-use of them in the next several decades. And then there's also the replacement chemicals. We also want to reduce the use of them as well. We're constantly trying to find better replacements of these CFCs.
Great. Well, I think unless there's anything else that folks would like to ask about the visualization that you've seen or about ozone around the Earth, I think that we'll wrap it up. Thanks for participating with us today. I wanted to direct you, if you visit the Science Bulletins site on amnh.org and you look for this visualization, there's other materials that can help support your use of it in educational programming. We've got a backgrounder which has detailed information on some of the topics that we've brought up today, a bit to help read the data visualization, and some extra links that might help in your interpretation and use of that. And feel free to reach out to any of us, reach out to us at the Science Bulletins Google Plus page or at sciencebulletins@amnh.org if you would like to gain access to materials that you've seen in this broadcast, or have any other lingering questions that we can address. So thank you, everyone. We will be holding more Hangouts throughout the year to highlight upcoming visualizations, and we'll get the word out about those as they come. So appreciate everybody participating. Thank you so much, Craig and Bryan, for joining us today, and we'll see you next time.
You're welcome, Laura.
Okay, thank you.
Great.